Okay then. So today, wow, no estoy siendo lo más productivo, mi amigo de mierda. So whatever, my nigga. Yeah, basically like, you know what I'm saying, like, mira, solo suena un oído. Ok, entonces después de 1 minuto y 31 segundos, vamos a comenzar con esto. Que chucha que me bloqueen, desmoneticen el vídeo. No importa. We're listening some fucking, you know, like shell, take it about booby, ok, sigamos. ¿Qué? ¿Dónde estamos? Oh, este videito, weón. Sí, no entendí ni mierda esto, weón. No entendí ni pinga esta explicación.
Here's a circle with an equilateral triangle.
Yeah.
Question: what's the chance of
I don't know, bro. No.
What is you smoking, man? That ain't pole. What is you talking, man? That ain't a pole. Illuminati, high society. We in this party and nobody invited me. We're going crazy. I always use my best sense, but it don't matter 'cause I stay on my fresh prince, maxing, relaxing, shooting some pool and playing some b-ball outside of the school. And girls with their top off outside of the pool and wits with the drop off outside of the lube. Just look stupid.
Poison. Oh, Poison did a lot of shit, huh? One D-bell curve and spooning, spoon it. What is a spoon? Like, como que hacer un, como que spoonear, como que girarlo, ¿no? Como que pasarlo. What the fuck is that, bro? Why would spoon? Span. Oh shit. Claro, girar. Yeah, como que I twist. Okay, I. Después hey, I twist.
When the sun goes down, I scream loud, sleep when I die. But I will never die.
Yeah.
My legacy is alive. When the sun goes down, I scream loud.
So pi is just like half a circle or what?
But I will never die. My legacy is alive.
No, nigga. Come on, bro. How you can add up individual points in a continuous model? Let's see this, bro. I don't know. This image. Yeah.
Service, if you hope that someday service, we got green in our eyes. Just follow my instrument. Moses not part the water with the cane. Drippers not make an art when I made it rain. Easy not get signed by Hogan Damon. Ran to Jacob and made the new Jesus chain. In Jesus' name, let the choir say, I'm on fire, A, that's a Richard Pryor say. And we'll annihilate anybody that violate. Ask any football you know, they admire.
My yeah. Yeah. How do you read? How do we read? Subset of element of. Oh. Yeah. Belongs to. What? So this shit is element of or belongs to? Oh, thing. Just. Okay, with single element, this with a whole entire set. Okay. Event is a subset of event. Event probability based less recall than the probability of A is less than or equal to. All that's missing is the reverend. All that's missing is a blessing. I hope God gives the mercy. What? Oh yeah, this is a subset of B. Okay. This is a subset. Yeah.
Picked you up out a dark place. Picked you up out a dark place.
There's also
outside of all time and space.
Symbol.
Float with me, baby, float with me.
Opposite
we had left the ground.
Subset, right?
Done surface. Meant to be, it's just written. Don't tell me how you feel, and then tell me you just kidding. Not dumb. It's meant to be, it's just written. Don't tell me how you feel, to tell me you just kidding. Cause if something isn't meant to be, you just need to.
And something isn't meant to be. Dun, 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 dun. Satellite connect to there's a blended party. Like your what? Your bus dragon idea. Oh yeah. Wow. You have to make assumptions. Your model sucks. So it suck. Claro. Model calculate human opinion vanishes. You're not tightly bound by the natural rules of logic and probability. Sort of ambiguity. Every question has a precise objective answer requirement. The book warns when the people find paradoxes probability were too valid. Mathematical methods give two totally different answers to the same question. Where's my water? Oh, fuck. Oh my goodness, bro. Yeah, what do you mean by this? I don't think that's what they mean, bro. Whatever. Okay, so yeah, I gotta watch this video. Definitely, I do.
Student comes
From here, okay?
and so this
Oh, this is like a plane momentum. I don't know. Bro, 1 fucking million
Side length
people
will be
just
exactly
watch
1/2.
this video without
This side length.
pics, without having any pics. Besides the beginning and a little valley here.
will be square root
For
of
some
3
reason,
halves.
they went just
So we could
apply
also say if it's a
Okay.
unit circle, what we're asking about is the probability that the length of our chord is bigger than the square root of 3. So just a simple question like anything else you might come across in some books, some list of exercises at the end. And let me show you how to solve it. It's really not that hard. Without loss of generality, you can assume that the first point is one of the corners of the triangle. If it wasn't, we could kind of rotate the triangle so that was the case. And then we weren't given any specifying information about the nature of the chord. So we'll assume that the next side is uniform somewhere around this circle. If the second point chosen was over there, we would have a chord that's shorter than the side lengths of the triangle. If it fell into this kind of critical region on the opposite side of the triangle, up here, that region, then the chord that you draw would be longer. And then similarly, if it was on this other side, it would be shorter. So, probability student, they're doing their homework. They say, what's the probability this is longer? Not a problem. It is going to be exactly 1 in 3 because the circle is evenly divided into 3 pieces. Oh, there's only one of those pieces that will give you longer chords. Said and done, not an issue.
So if any random chord, there's a 1/3 chance it's going to
Random
have
chord?
that long.
Yeah,
Yeah.
no paradox to be found. In fact, let's verify this empirically. I ran a simulation. Essentially what I do is I choose a random pair of points somewhere on the circle, I connect them, and then I'm going to count whether or not that ends up longer than what we need, and then basically ask the proportion where that's the case. And I'll color it blue whenever it's longer, and then white whenever it's shorter. I'm just going to have this simulate a whole bunch. It'll do on the order of 1,000. And this ratio will be telling us what proportion of them are longer than the length we care about. And
Look at
yeah, it seems
that.
like it's going roughly on the order of 1/3, so 0.33, kind of oscillating 0.44. So we did it theoretically, we did it empirically, we have an answer. So another student comes in, they're doing the same homework, and they say, you know, the funny thing about chords is that they are uniquely determined by their midpoint in the circle.
Midpoint is circle.
So they say, if you give me a midpoint
Is that a midpoint?
of the chord, they say actually there's one and only one chord for which that would be the midpoint. You draw the line that's
Say that
actually
shit
there's
again.
one and only
There's-
one chord
One chord,
for which that would be the midpoint.
for which that would be the
You draw the
midpoint.
line that's perpendicular to the radius between that midpoint and the center of the circle, and that will give you one and only one chord. So then they go to their
Okay.
triangle and they try to reason, when is it the case that our chord is going to be shorter than the side lengths of that triangle? And what they can also do is come up with a pretty geometric argument where they think about the circle that's inscribed in that triangle. Got sort of a Deathly Hallows vibe going on here. And what they're able to conclude is basically when the center of the chord is on the inside of that inscribed circle, then the relevant chord is going to end up longer than the side length of the triangle. We can kind of see that there. But if the random midpoint that you chose was on the outside of that inscribed circle, the chord you find will be shorter. And length of the triangle. So you can kind of see that there. But if the random midpoint that you chose was on the outside of that inscribed circle, the chord you find will be shorter.
Claro.
And we simply say, okay, what is the size of that circle? And
Fucking no.
we actually drew one of our lengths earlier and concluded that it was 1/2. So we know this inner circle has a radius which is 1/2. So that inner circle has an area.
What is the purpose of this shit? I don't fucking know what you're talking about. What is the purpose of this bullshit, man? What? Stupid different. The purpose of the fucking Bertrand, right? Bertrand's paradox. How the fuck is that related to probability? Some sort of weird ass geometry. But I don't know, man.
1/4.
I don't know, bro. I mean, what the fuck? I don't get it yet. I don't get it yet. Actually, frustration does from us in the image one look like an absolute alien. Formulas? What formulas, bro? Oh my god, this nigga's hallucinating again. What are you looking? What you are looking at? No, this is not the Morgan law. What the fuck? Bro, I hate this shit for real. This motherfucker. There's absolutely no limit. Huh. Being 7'5" interesting. 6 Sigma in business. Huh. Wow. What? What do you mean? What do you even mean? 6 Sigma. Wow. What is this? I don't get it. Motorola. Looks so interesting. Hmm. 3.4 times out of every million tries. Cool, right? Huh. Radiance, yeah. Oh. Superset. Wow. What? Oh, wait, what? The symbols for sets work exactly like the greater than and less than signs for it. I never said that, but alright. Means subset. So yeah, dogs is less than the mammals. Mammals are greater than dogs. Right? Yeah. Includes dogs. Wow. The upper mouth of the symbol always points to the bigger group. The upper mouth. Yeah, okay. Wow. Yeah, literally like this. Yeah, cool. Whatever, fuck you, bro, because I don't think I need this. I don't know what the fuck is this. I mean, probability, blah, 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 but alright. A brief history of probability. Okay. Stop.
I ain't say the right thing back then. I would just pray, you know what I meant. I would pray, you know where I've been. Why you ask, you know where I've been. Why you making me tell evidence? First night you was hesitant. I promised to never, ever fall in love again. I can't trust it the way I can't love it the way I used to. I can't love it the way I used to. I can't feel the way I do to. I can't trust it the way I can't love it the way I used to. I can't love it the way I used to. I can't feel the way I used to. Love is best in the honeymoon stage. Pray the honeymoon on last for days. Love is best in the honeymoon stage. Pray this honeymoon can last for days. Ask for me, ask for yeah. If you tired of getting ripped off, go to top door to walk off and ask for yeah. I need this honeymoon to
Games a chance to
last
put
days.
in
Go
Oh, really?
walk off and ask for yeah.
Blackjack or
I
what?
need this honeymoon stays and last for
But it's
days.
the thing of the really so stupid. Why
Ask for yeah. I
What number
need
system
this
they used?
honeymoon to
Hexadecimal.
last days.
Hexadecimal. Alright.
You know where I stand, pumping on new love. It's nothing to rush, but I knew you was moving in when I saw your toothbrush. You fell in love, a new love. They say it's nothing to rush, but we knew you was moving in when I saw you toothbrush. Picked you
He's
up
nervous.
out a dark
I've always
place.
been smart, right?
Picked you up out a dark place. Outside of all time and space.
Generated
Float with me, baby, float with me.
technology.
We had left the ground. We had left the
Girolamo
ground. Never coming back. Never coming back. Never coming back. We ain't left the ground. Never coming back. Never coming back. Never coming back. I'ma be like the Loch Ness. Never coming back. Never coming back. Never coming. And you ain't coming back. Never coming. We ain't coming back. Never coming. And you ain't coming back. Never coming. And we ain't coming back. Never coming. We ain't coming back.
Never coming back. Cada no es una coin, a crypto coin, cryptocurrency. I don't need to know this either, right? Touches upon several interesting probability questions. Cool. Fermat on Pascal. Large numbers. Wow, yeah. Large numbers. País. Lagrange. The Moivre. Limit theorem. Wow, look at that. We don't have like a limit theorem in calculus as well.
When had you take time to find for me? When did you put me before you put yourself? When did you wait for me to get past myself? When did you learn something, let me last my mouth? Always. Always. Always.
Natural sound.
Always. When do you have patience when I don't know? When were you there when there was nobody else? When had you love not sad the way I felt? When you were loving me beside myself. Always, always,
Kolmogorov.
always,
Kolmogorov sounds like a really cool guy.
always.
The Smirnov test. Oh, I heard about that. This nigga's Peruvian, bro. What the fuck? This shit's made of floods.
Pouring down.
Alright.
Tears come
Russian Empire.
pouring down. Tears come pouring down. When my train of thought ran off the track, when I was something off the
my
map,
train of thought
when
off
I
the track.
something off the tat.
That was a
I
good
had
one. That was a
less
good one,
about-
bro. So, bro, so shut the fuck up. Physical phenomenon pervasively in science. So at the 21st century, no shit happened, huh? Science and engineering. Okay. Finally, we got to conditional probability. Let me see a really short clip. Yeah. Class 12. What the fuck is this in
But then what do you say, like, well, what is the
Rogan?
probability that Donald Trump wins re-election? That's not going to happen an infinite number of times. You're not going to do the experiment. Or even better, what would...
No, he was talking about that. Yeah.
Conditional probability is the probability of an event occurring given that another event has already occurred. It denoted as, which means the probability of
The probability of A such that B has happened.
event A given that the event
Yeah.
B
that's
has
the
occurred. Conditional probability is used in many real-world applications.
I
For
know,
example,
okay.
determining the
I
probability
remember
of a
that.
person having a disease given a positive test result. Another example is updating probabilities in machine learning and data analysis based on new evidence.
Now, conditional probability is... I think I already asked this, but okay. Doesn't matter. It's called theorem, right? Or something else. By using theorem. Yeah. Yeah. I'm not hallucinating. You fucking hallucinated, bro. You don't even recognize it. Recognizes it. No, nigga. Oh, specify unambiguously the probabilistic model. Hmm. Hmm. Yeah. Okay. Cool. Fuck yeah. Su madre. Su puta madre. Ay, la mierda, man. Ya no estoy tocando el micro, weón. Jeje. 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 Ustedes no escuchan la diferencia, pero yo sí. Yo sí, cuando muevo esta huevada. Sí, cuando juego esto se escucha caer risa. Wow, se escucha diferentísimo. Y creo que ese sonido sonó bastante. Creo que ese golpe sonó bastante. Bueno, estoy matando tiempo, carajo. Let's get to it, bro. Hold on. 1, 2, 3, 4, 5, 6. Wait, hold the fucking on. We already did the first lecture. In it. Right? Yeah, fuck yeah. And that's actually the second lecture. So, let's continue.
The following
Oh my goodness, bro, hold on.
content is provided under a Creative Commons license.
Okay, where are we at?
That's the material until our
Remember,
first quiz. And some of you may get by without being too systematic about following the material, but it does get substantially harder afterwards. And I will keep restating that you do have to read the text to really understand the material.
Daily, man. This is not enough.
Okay, so now we can start with the real part of the lecture. Let us set the goals for today.
Nice.
So probability theory is a framework for dealing with uncertainty, for dealing with situations in which we have some kind of randomness. So what we want to do is, by the end of today's lecture, to give you anything that you need to know how to set up, what does it take to set up a probabilistic model, and what are the basic rules of the game for dealing with probabilistic models.
Yeah.
So by the end of this lecture, you will have essentially recovered half of this semester's tuition, right? So we're going to talk about probabilistic models in more detail, the sample space, which is basically a description of all the things that may happen during a random experiment, and the probability law, which describes our beliefs about which outcomes are more likely to occur.
No asustes, mierda, puta madre. Puta madre, weón. Firme, weón.
Compared to other outcomes. Probability laws have to obey certain properties that we call the axioms of probability. So main part of today's lecture is to describe those axioms, which are the rules of the game, and consider a few really trivial examples. Okay, so let's start with our agenda. The first piece in a probabilistic model is a description of the sample space of an experiment. So we do an experiment,
So cool, so crazy.
and by experiment we just mean that just something happens out there.
Yeah.
And that's something that happens.
An
It
event.
could be flipping a coin, or it could be rolling a die, or it could be doing something in a card game. So we fix a particular experiment, and we come up with a list of all the possible things that may happen during this experiment. So we write down a list of all the possible outcomes. So here's a list
Just
of
the
all the
sample
possible
space
outcomes
or
of the
sets?
experiment.
No, that's a set.
I used the word list, but if you want to be a little more formal, it's
Set.
better to think of that list as a set.
Yes, sir.
So we have a set. That set is our
fucking go.
sample space. And it's a set whose elements are the possible outcomes of the experiment. So for example, if you're dealing with flipping a coin, your sample space would be heads. This is one outcome.
Oh, my
Tails
bad.
is one outcome.
That was a die.
And this set, which has two elements, is the sample space of the experiment. Okay, what do we need to think about when we're setting up this sample space? First, the list should be mutually exclusive, collectively exhaustive. What does that mean? Collectively exhaustive means that
Que puedes tener varios.
no matter what happens in the experiment, you're going to get one of the outcomes inside here. So you have not forgotten any of the possibilities of what may happen in the experiment. Mutually exclusive means that if this happens, then that cannot happen. So at the end of the experiment, you should be able to
So collectively exhausted significa que tienes varias opciones.
point
¿no?
out to me just one, exactly one of these outcomes and say, this is the outcome that happened. Okay, so these are sort of basic requirements. There's another requirement which is a little more loose. When you set up your sample space, sometimes you do have some freedom about the details of how you're going to describe it. And the question is, how much detail are you going to include? So let's take this coin flipping experiment and think of the following sample space. One possible outcome is heads. A second possible outcome is tails, and it's raining. And the third possible outcome is tails, and it's not raining. So this is another possible sample space for the experiment where I flip a coin just once. It's a legitimate one. These three possibilities are mutually exclusive and collectively exhaustive. Which one is the right sample space? Is it this one or that one?
What do you mean?
Well, if you think that my coin flipping inside this room is completely unrelated to the weather outside, then you're going to stick with this sample space. If, on the other hand, you have some superstitious beliefs that maybe rain has an effect on my coins, you might work with a sample space of this kind. So you probably wouldn't do that, but it's a legitimate option, strictly speaking.
Wow.
Now, this example is a little bit on the frivolous side, but the issue that comes up here is a basic one that shows up anywhere in science and engineering. Whenever you're dealing with a model or with a situation, there are zillions of details in that situation. And when you come up with a model, you choose some of those details that you keep in your model, and some that you say, well, these are irrelevant, or maybe there are small effects, I can neglect them, and you keep them outside your model. So there's definitely, when you go to the real world, there's definitely an element of art and some judgment that you need to do in order to set up an appropriate sample space. So an easy example now. So of course, the elementary examples are coins, cards, dice. So let's deal with dice, but to keep the diagram small, instead of a six-sided die, we're going to think about a die that only has 4 faces. So you
4 faces. Oh yeah, the tetrahedral.
can do that
pyramid.
with a tetrahedron, it doesn't really matter. Basically, it's a die that when you roll it, you get a result which is 1, 2, 3, or 4. However, the experiment that I'm going to think about will consist of 2 rolls of a die. Crucial point here.
Is there
I'm
a
rolling the
pentahedral? I'm curious. Extant. Pentahedral. What the fuck? Pentahedral. What the fuck? Does the share exist? at all? Kind of. Wow. It's absolutely crazy. Crazy.
Die twice, but I'm thinking of this as just one experiment, not two different experiments, not a repetition. Of twice of the same experiment. So it's one big experiment. During that big experiment, various things will happen, such as I'm rolling the die once, and then I'm rolling the die twice. Okay. So what's the sample space for that experiment? Well, the sample space consists of the possible outcomes. One possible outcome is that your first roll resulted in 2, and the second roll resulted in 3, in which case the outcome that you get is
5.
this one, a 2 followed by 3. This is one possible outcome.
Yeah.
The way I'm describing things, this outcome is to be distinguished from this outcome here,
3, 2.
where a 3 is followed by 2.
Yeah.
If you're playing backgammon, it doesn't matter
Backgammon.
which one of the two happened. But if
I
you're
wanna play
dealing with a
backgammon.
probabilistic model that wants to keep track of everything that happens in this composite experiment, there are good reasons for distinguishing between these two outcomes. I mean, when this happens, it's definitely something different from that happening. A 2 followed by a 3 is different from a 3 followed by a 2. So this is the correct sample space for this experiment where we roll the die twice. It has a total of 16 elements, and it's, of course, a finite set. Sometimes, instead of describing sample spaces in terms of lists or sets or diagrams of this kind, it's useful to describe the experiment in some sequential way. Whenever you have
Neural networks?
an experiment that consists of multiple stages,
Yeah.
it might be useful, at least visually, to give a diagram that shows you how those stages evolve. And
Sequential description. What is wrong with this? Oh, my nigga. Sequence. Wow. Sequential description. Word.
that's what we do by using a sequential description or a tree-based description, by
Tree-based.
drawing a tree
tree.
of the possible evolutions during our experiment. So in this tree, I'm thinking of a first stage in which I roll the first die, and there are 4 possible results, 1, 2, 3, and 4. And given what happened in the first, let's say in the first roll, suppose I got a 1, then I'm rolling the second die, and there are 4 possibilities for what may happen to the second die, and the possible results are 1, 2, 3, and 4 again. So what's the relation between the two diagrams? Well, for example, the outcome 2 followed by 3 corresponds to this path
Yeah.
on the tree. So this path corresponds to 2 followed by a 3. Any path is associated to a particular outcome. Any outcome is associated to a particular path. And instead of paths, you may want to think in terms of the leaves of this diagram. Same thing.
What?
Think of each one of the leaves as being
Oh, leaves. Oh, yeah. That's for a tree. Wow. Super duper cool. Seguimos mierda.
being one possible outcome. And of course, we have 16 outcomes here. We have 16 outcomes here. Maybe you noticed a subtlety that I used in my language. I said I roll the first die, and the result that I get is a 2. I didn't use the word outcome. I want to you noticed a subtlety that I used in my language. I said I roll the first die, and the result that I get is a 2. I didn't use the word outcome. I want to reserve the word outcome to mean the overall outcome
The
at
final.
the end of the
Final.
overall
Yeah.
experiment. So 2,3 is the outcome
That's
of
the
the
only
experiment.
outcome.
The experiment consisted of stages. 2 was the result in the first stage, 3 was the result in the second stage. You put all those results together and you get your outcome. Okay, perhaps we are splitting hairs here, but it's useful to keep the concepts right. What's special about this example is that besides being trivial, it has a sample space which is finite. There's 16 possible total outcomes. Not every experiment has a finite sample space. Here's an experiment in which the sample space is infinite. So you're playing darts, and the target is this square, and you're perfect at that game, so you're sure that your darts will always fall inside this square. So, but where exactly your dart will fall inside that square, that itself is random. We don't know what it's going to be. It's uncertain. So all the possible points inside the square are possible outcomes of the experiment. So a typical outcome of the experiment is going to be a pair of numbers, x, y, where x and y are real numbers between 0 and 1. Now there's infinitely many real numbers.
Wait. But x is greater than 0, greater or equal than 0, and y is less or equal than 1, right?
The experiment is going to be a pair of numbers, x, y, where x and y are real numbers between 0 and 1. Now there's infinitely many real numbers. There's infinitely
both are
many points in the square.
0 and 1.
So this is an example in which our sample space is an infinite set.
How the fuck can I say that like this? Like this is separate. Like only x is greater than 0 and y is less than 1. How can I say that? I don't know.
Okay, so we're going to
Maybe that's what's
revisit
happening.
this example a little later. Okay, so these are two examples of what a sample space might be in simple experiments. Now, the more important order of business is now to look at those possible outcomes and make some statements about their relative likelihoods. Which outcome is more likely to occur compared to the others? And the way we do this is by assigning probabilities to the outcomes. Well, not exactly. Suppose that all you were to do was to assign probabilities to individual outcomes. If you go back to this example and you consider one particular outcome, let's say this point, what would be the probability that you hit exactly this point to infinite precision? Intuitively, that probability would be 0. So any individual point in this diagram, in any reasonable model, should have 0 probability. So if you just tell me that any individual outcome has 0 probability, you're not really telling me much to work with. For that reason, what instead we're going to do is to assign probabilities to subsets of the sample space, as opposed to assigning probabilities to individual outcomes.
Right.
So here's the picture. We have our sample space, which is omega, and we consider some subset of the sample space, call it A, and I want to assign a numerical probability to this particular subset, which represents my belief about how likely this set is to occur. Okay, what do we mean to occur? And I'm introducing here a language that's being used in probability theory. When we talk about subsets of the sample space, we usually call them events as opposed to subsets. And the reason is because it works nicely with a language that describes what's going on. So the outcome is a point. The outcome is random. The outcome may be inside this set, in which case we say that event A occurred, if we get an outcome inside here. Or the outcome may fall outside the set, in which case we say that event A did not occur. So we're going to assign probabilities to events. And now, how should we do this assignment? Well, probabilities are meant to describe your beliefs about which sets are more likely to occur versus other sets. So there's many ways that you can assign those probabilities, but there are some ground rules for this game. First, we want probabilities to be numbers between 0 and 1 because that's the usual convention. So probability of 0 means we're certain that something is not going to happen. Probability of 1 means that we're essentially certain that something is not going to happen. So we want numbers between 0 and 1. We also want a few other things. And those few other things are going to be encapsulated in a set of axioms. What axioms means in this context, it's the ground rules that any legitimate probabilistic model should obey. You have a choice of what kind of probabilities you use, but no matter what you use, they should obey certain consistency properties, because if they obey those properties, then you can go ahead and do useful calculations and do some useful reasoning. So what are these properties? First, probabilities should be non-negative. Okay? That's our convention. We want probabilities to be numbers between 0 and 1, so they should certainly be non-negative. The probability that event A occurs should be a non-negative number. What's the second axiom? The probability of the entire sample space is equal to 1. Why does this make sense? Well, the outcome is certain to be an element of the sample space, because we set up a sample space which is collectively exhaustive. No matter what the outcome is, it's going to be an element of the sample space. We're certain that event omega is going to occur. Therefore, we represent this certainty by saying that the probability of omega is equal to 1.
100%.
Pretty straightforward so far.
What am I, bitch?
The more interesting axiom is the third rule. Before getting into it, just a quick reminder. If you have two sets, A and B, the intersection of A and B consists of those elements that belong both to A and to B, and we denote it this way. When you think probabilistically, the way to think of intersection is by using the word and. This event, this intersection, is the event that A occurred and B occurred. If I get an outcome inside here, A has occurred and B has occurred at the same time. So you may find the word and to be a little more convenient than the word intersection. And similarly, we have...
Let me see something, though, because this is applied probability. I'm going to use statistics. You know what I mean? Random variables. I don't think this shit is... I mean, it's gonna help me though, but I don't know. This shit's statistics. You know what I mean? Hold on. Just give me 1 second. Statistics. Oh shit. I don't know if this is different. I think this shit's different, bro. It's statistic for applications. Oh my fucking goddamn, bro. Fuck you, bro. Oh, well, this is... I don't know, I'm just curious now, bro. Yep. Testing goodness of fit, regression based on statistics. Any prerequisite? Ensemble in algebra, matrices. Nah, I don't think I need this. Huh. Fall 2026. Well, whatever. I think this course helps me anyway.
Some notation for the union of two events, which we write this way. The union of two sets or two events is the collection of all elements that belong either to the first set or to the second or to both.
Yeah.
When you talk about events, you can use the word or. So this is the event that A
A or
occurred
B.
or B occurred. And this or means that it could also be that both of them occurred.
And
Okay, so now that we have this notation, what does the third axiom say? The third axiom says that if we have two events, A and B, that have no common elements, so here's A, here's B,
no common
and
elements.
perhaps this is our big sample space. The two events have no common elements. So the intersection of the two events is the empty set. There's nothing in their intersection.
Right.
Then the total probability of A together with B has to be equal to the sum of the individual probabilities. So the probability that A occurs or B occurs is equal to the probability that A occurs plus the probability that B occurs. So think of probability as being cream cheese.
There's a microwave, right? It's kind of cool. They have microwaves in the
You have 1 pound of cream cheese, the total probability assigned to the entire sample space, and that cream cheese is spread out over this set. The probability of A is how much cream cheese sits on top of A. Probability of B is how much sits on top of B. The probability of A union B is the total amount of cream cheese sitting on top of this and that, which is obviously the sum of how much is sitting here and how much is sitting there. So probabilities behave like cream cheese or they behave like mass. For example, the total mass over the mass of a set, if you think of some...
Dijo, no me va a pasar. No sé qué hacer ahora. Y bueno, se fue por el otro lado. Bueno, te pudiste haber ido por atrás. ¿Te imaginas si iba por atrás, weón? Por el culo. Si iba por atrás.
Like mass.
Ay. I'm sorry, profe.
For example, the total mass
se va al salón, se sale de la universidad y ya está, bro. Y abandona la carrera.
Mass of a set, if you think of some material object, the mass of this set consisting of two pieces is obviously the sum of the two masses. So this property is a very intuitive one. It's a pretty natural one to have. Okay.
That shit was just 15 years ago. It looks so
are these axioms enough for what we want to do? I mentioned a while ago that we want probabilities to be numbers between 0 and 1. Here's an axiom that tells you that probabilities are non-negative. Should we have another axiom that tells us that probabilities are less than or equal to 1? It's a desirable property. We would like to have it in our hands. Okay, why is it not in that list? Well, the people who are in the axiom-making business are mathematicians, and mathematicians tend to be pretty laconic. You don't say something if you don't have to say it.
Laconic.
Right.
And this is the case here. We don't need that extra axiom because we can derive it from the existing axioms. Here's how it goes.
But do we really need to mention those fucking extra actions?
One is the probability of the entire sample space. Here we're using the second axiom. Now the sample space consists of
of every set. Of the addition of
A
every set,
together with the complement of A.
With the complement, right?
Okay, so this is when I write the complement of A, I mean the complement of A inside the set omega. So we have omega, here's A, here's the complement of A, and the overall set is omega. Okay, now what's the next step? What should I do next? Which axiom should I use? We use axiom 3 because a set and the complement of that set are disjoint. They don't have any common elements. So axiom 3 applies, and tells me that this is the probability of A plus the probability of A complement. In particular, the probability of A is equal to 1 minus the probability of A complement. And this is less than or equal to 1. Why? Because probabilities are non-negative by the first axiom.
Okay, say that shit again, bro.
The probability of A is equal to 1 minus the probability of A complement. And this is less than or equal to 1.
Okay. Yeah,
why?
Yeah. Because there's no 1, bro.
Because probabilities are non-negative by the first axiom.
Yeah.
Okay, so we got the conclusion that we wanted. Probabilities are always less than or equal to 1.
Yeah,
and this is a simple consequence of the 3 axioms that we have. This is a really nice argument because it actually uses each one of those axioms. The argument is simple, but you have to use all these 3 properties to get the conclusion that you want. Okay, so we can get interesting things out of our axioms. Can we get some more interesting ones? How about the union of 3 sets? What kind of probability should it have? So here's an event consisting of 3 pieces. And I want to say something about the probability of A union B union C. What I would like to say is that this probability is equal to the sum of the 3 individual probabilities. Yeah. How can I do it? I have an axiom that tells me that I can do it for 2 events. I don't have an axiom for 3 events. Well, maybe I can massage things and still be able to use that axiom.
Same shit, bro. Just do it. Just fucking do it. Ay, qué wea la gente, hermano, que... Es que, I don't know. Es que me acuerdo de los huevones que repitieron cálculos. Es que tarados también, pero seguro, es que estoy seguro que ni practicaban, ni... Tanto así que les fue mal el penúltimo examen, que ya ni siquiera fueron a la final. Y no sé, me da pena, weón. O sea, merecido, totalmente merecido esos goles, pero me da pena, hermano. Me da pena. Y ahora pues, igual muy orgulloso por mí mismo. Mentira, muy orgulloso. Porque pasé, tío. Hermano. Ok. No sé, un recuerdito.
Axiom. And here's the trick. The union of...
Okay, bye.